Hello, welcome to our webinar. On this occasion, we will be talking about introduction to acoustic modems, particularly our acoustic modems, but in general, what are the criteria that you need in order to choose the right equipment? My name is Francisco Bustamante. I'm the Senior Operations Manager for EvoLogics, and I will be presenting the different criteria that we use and when we have a discussion with a customer, how to select equipment that is best for different applications. In this presentation, I would like to provide a practical approach based on these criteria that we use and provide you some general guidelines on how to select modems. We will also touch on some application examples. We'll also show some tools that can be used to familiarize yourself with the use of acoustic modems, for example, our acoustic modem emulator. If you have any questions throughout the presentation, you can use the Q&A button that is at the bottom of the screen in Zoom to write your questions to us. At the end, we will have some time to reply to you and hopefully help you with these questions that you might have. Otherwise, we will also provide you with our contact information and you can get in touch with us at any time later. By the end of this presentation, you should be able to answer the following questions. What can you do with an acoustic modem? Why would you like to use an acoustic modem? What criteria is important in selecting an acoustic modem? And what challenges and solutions to these challenges exist? So what do you do with an acoustic modem? You can basically have a sensor connected to a computer via a cable, or you can have this sensor connected to a computer via a underwater modem. In the same way that you would have a sensor or some data source connected to a computer or connecting several sensors with Wi-Fi or Bluetooth, these modems basically substitute the cable connection. Of course, not the same way that you would have a cable, because there are some other issues that we will later discuss that you have to take into consideration, but basically this is what they do. So what can you transmit with these modems? So you can have sensors such as ADCPs, video, CTDs, pressure sensors, cameras, DVLs, hydrophones. There's a multitude of sources that you can have. You can install the modems in your AUVs or other vehicles. As long as you have any digital output, you can put this information in our modems. There are some sensors, however, that have analog outputs. And in those cases, you need some kind of intermediary that will convert this analog information into digital data in order to be able to transmit it with our modems. So why do you want to use an acoustic modem? There are many reasons, but one is that you can basically expand the range of the operations underwater. So if you are restricted to having a cable, then the maximum range is obviously what you have with a cable. Cables become expensive, impractical, they can break. And having a modem, you can establish a quick link and you don't need to have a permanent cable installed. You can simply have your 2 points where you are transmitting. And this can be done relatively easy. So this is the main reason why you would want to use acoustic modems. You can expand the range and it gives you advantages over cables in certain scenarios, or there are scenarios where you cannot use cables simply because they are too long or they are located in an area where there is traffic or it's difficult to place at certain depths. The applications are many. You can, as I mentioned before, use them for unmanned underwater vehicles. Environmental monitoring is a very common application. You have sensors that transmit data autonomously to the surface. But there are others such as structure monitoring, offshore industry, for example, underwater cameras, fishing trawls. And as I mentioned before, if you have a digital source of information, you can transmit the modem. So the possibilities are endless and are hand in hand with your imagination and your needs. Multipath propagation is the biggest problem, I would say, when you have underwater acoustic transmissions. So you basically have one sender and one receiver. And you would imagine that if you send a signal, the receiver will get only one signal on its end, but that's not what happens. The signal can be reflected on the seafloor, can be reflected on the surface. It can also be reflected inside the water when there are layers that are caused by temperatures, by different salinities, and so on. And so what happens is that the receiver basically receives multiple copies of the same signal. So interference, like having echoes in a closed room. And in order to decode the signals, we have to use some creative tricks. And this is in order to achieve the required reliability and data bandwidth. However, there are some general criteria that are important to selecting a modem. For example, the two most important factors that we always want to know is what is the maximum transmission distance that you will have. And the other is what is the depth at which these devices will be operating. So and importantly also, if one of the devices is at the surface, will the other one be placed directly below it? Will it have an horizontal displacement or something in between? So these three aspects are important. And this is because we have, and other manufacturers also have devices that are using different frequencies. So higher frequencies allow you to transmit more data, but then the range is lower. So you need lower bandwidth, lower frequencies to achieve a longer range. And also the devices have different directivity characteristics. So here we see, for example, low frequency devices, our 7 to 17 kilohertz device can have range of up to 8,000 meters. And then we have other devices that are high frequency that can only achieve up to 1,000 meters. And our high speed modem can only do 300 meters. And at the same time, you have different ways in which the signal is propagated. So we have horizontally omnidirectional devices. Those propagate toroidally like a donut from the transducer. You have directional devices that must be pointed at each other. You have wide angle, hemispherical, and omnidirectional. So the combination of which devices you need will depend on how far away you are and what's the relative position of one device to the other. So coming back to the directivity, so if we have a vertical transmission, you want to use a directional device because you have these cones from each device, and as long as these cones are overlapping, as shown in the left picture, then you will have a successful transmission. On the other hand, if you have devices that are placed at around the same depth and with some horizontal distance, then you want to use a horizontally omnidirectional device that will provide the communication overlap as required. There are different options in terms of power requirement and optimization options. So you can have different data sources. For example, you can connect directly to a sensor, but you can also connect to an embedded device, an embedded system that collects the data from one or more sensors and does some pre-processing. Or a camera, and this is one important aspect to take into consideration. Then you need to consider how will the system be activated. In some cases, you have systems that operate only for a few hours to a day or two maximum. In that case, this is not such a consideration. But in some cases, you have systems that need to operate autonomously for 2 or 3 years or even longer. And in that case, it's important to know, well, the system needs to go to a standby mode, to a sleep mode. And then how are we going to get the system to operate? And this can be done with either a sensor that activates this device, or we can send acoustic signals. Then if you have a frequent transmission and you have large data packets and your deployment time is long, this all translates into power consumption higher power consumption. So the longer your system is operating, you need to take this into consideration. And in some cases, it may be necessary to do some optimizations. As I mentioned, the power consumption depends on the time. So even if you have a system that is not transmitting data, it's just waiting, there is a power consumption. This can be minimized to be lower over time or at a minimum, but still you are consuming power. And then of course you have your data transmissions that probably make the bulk of your power consumption. But the energy consumption will depend on both these factors, how much data you are transmitting and how long will the system will be operating. In order to solve the power requirements, we can use either internal batteries or external power. Internal batteries are practical because you only have one device. It's easy to deploy, but then your battery capacity is limited. It's better for short deployments, as I mentioned, from a few days to maybe up to 3, maximum 4 months. That's depending on how much you will be transmitting, but this is it's a rule of thumb. And external power is required in most long-term applications. So if you have an application that requires 1, 2, 3 years or more, then you need an external battery with the required capacity and size, of course, and this will probably be much larger than what can be integrated into the modem. So how can you reduce the power consumption? This is a very important thing for long-term deployments. And the first option is to use an acoustic wake-up module. This will put the equipment in standby mode. So as when there's no transmissions, the power consumption is decreased considerably. The other things you can do is to reduce the frequency of transmissions. So instead of transmitting every 5 minutes or every hour, you can transmit every 8 hours or every day or every week. Of course, this depends on how your application requires the data, but transmitting fewer times will reduce the power consumption, in particular because you can also optimize the overhead, reduce the overhead. You can optimize the data types. So maybe your sensor is producing some text data, and this can be compressed and can be reduced to some other data types that are more optimal for transmission. And if you really have a lot of data and yeah, you're probably going to be operating on a longer term, there's also the option of doing some pre-processing. So analyzing the data at the source and only transmitting the relevant or summarized information, maybe having some alarm values or averaging, etc. We have another webinar about sensor integration where we also discuss this in more detail. There are environmental factors to consider when selecting a modem. So maybe you are in shallow water. This is water that is less than 50 meters depth. And if you have, for example, even lower than 20 meters or 10 meters, these effects only increase. But shallow waters will reduce the effective range of acoustic modems. You have higher multipath propagation, and then this means that a modem that normally has up to 1,000 meters maximum range, maybe in these conditions, will see 40–50% reduction in the maximum range. So what are the alternatives? You can select a device that has a lower frequency to operate. So instead of having a device that only has 1,000 meters maximum range, you can use a device that has 3,000 meters maximum range. Or the other option is you can increase the transmit power. But if you have a long-term application, this might not be the optimal solution. Another effect is you can have strong water stratification. That means the water layers that are generated in the water body, so sudden jump in water temperature or salinity. This has a very similar effect to having shallow waters. So it will reduce your range, it will increase your multipath propagation, and there are some solutions that we can propose. So maybe using a different directivity is an option. In particular, if you're doing vertical transmissions, you can select a directional beam, and this will increase the effectivity. you can increase the transmit power, or sometimes very simple, you can try placing the equipment at a different water depth. So the surface unit, simply by placing it 2 or 3 meters lower than you were operating, suddenly you are below this strong stratification layer, and then your performance can increase dramatically. Another factor that can happen is you have dissolved gases in the water body. So air bubbles or maybe gases from plant decomposition. This will generate higher attenuation, signal loss. And there are a few options you can try. So increasing transmit power or placing the equipment at different depths or different positions. But in some cases, this can also be a very strong effect. And then you might need to think about different solutions. Some example applications, and based on what we have done for previous customers, common applications. So deep water observatory is a very common application. In particular, we are talking about an example where the water depths were up to 3,000 meters. This observatory has multiple sensors on the seafloor connected to an embedded system, so pressure sensor, CTD, camera, and this device is, or our modem is with an optional wake-up module on the surface buoy and on the seafloor. So when either one of the modems, either the surface or the seafloor unit, start a communication, they can wake up the other end and transmit data activated either locally when the sensors or the embedded system provides data, or via a remote signal. In this particular application, the surface buoy does not only have the modem, but it also is connected to a satellite modem. So the data can be transmitted from the seafloor directly to an office anywhere in the world. Second example is using the modems, for example, to control fishing trawl doors. This can be used for, instead of having just the tension on the cables of the trawl, control where the door is positioned, you have the option of sending an acoustic signal and have these doors that actuate by themselves with some battery power, of course. And then you can control very precisely where they are positioned in the water body. So you can select the depth, you can say when they need to turn and so on. This case we used, it's for applications with depths up to 2,000 meters and distances up to 3,000 meters, sending and receiving information to the doors. And the solution we proposed was using long-range directional modems. So basically the vessel unit is pointing towards the trawl doors, and the trawl door units is also pointing towards the vessel. And this is an application where wake-up module is not required. The deployment time is only 6 to 7 hours, and the normal battery will provide enough power to operate during this time. Finally, also a very common application is mission control of AUV operation. So in this case, it's very common to have water depths up to 100 meters, even more, but commonly, and then distances of 600 meters, frequently also more. And we can, with the modems, send commands to the vehicles, read status information. And if you combine the acoustic modem with a USBL transceiver that does both the positioning and the transmission, you can also have the positioning and navigation of this vehicle. It's common in this kind of application to use a horizontal omnidirectional beam. For example, the 18 to 34 kilohertz unit. And as I mentioned before, using the USBL provides you also with this simultaneous positioning information. So this is basically the range of, or the criteria that we discuss with any project where we start with a customer. Of course, what is the maximum distance, depth? These are common criteria. But we also have some features in the modems that can help the user be more effective with their application. So for example, advanced data management. This means that the user can simply put the data in the modem, and the modem takes care of all the retransmissions, error correction, as you would expect, for example, with a Wi-Fi connection. All of this happens automatically. You can have multiple logical channels, which is good if you have multiple sensors. You can define different priorities, for example. And you can also have this transparent link, basically. You connect the modem as if you were connecting a cable, and you don't have to take care of anything particular. We have also developed some special protocols to take transmission delays into consideration. Some sensors are sensitive, or their software rather is sensitive to timeouts. And since you are transmitting in water, the lag is higher, much higher. So we have some workarounds where we basically trick the sensor and the computer into thinking they are talking to each other directly at a shorter distance, but we are doing some magic in between. So by using the same signals for positioning, we also increase the possibilities. As I mentioned, you can navigate with AUVs to the positioning. And we also have developed some networking options for our modems, so relaying for longer distances, or broadcasting, or even some mesh configuration networks are possible using acoustic modems. There are multiple options available for our devices in particular that can be interesting depending on your application. So for example, you can have multiple interfaces and connectors. And this can be interesting if you have multiple sensors and you don't want to have one modem for each. You can connect multiple sensors to one modem and use one modem for the transmission. We mentioned before the acoustic wake-up model, but this is very important for power saving during idle transmission times, and any long-term application will benefit from this module. We have optionally a releaser module that can be installed inside the modem or integrated into the housing. So you have now a unit that has both a modem. You can also integrate the battery and the release, and this will come back to the surface with an acoustic command when you have finalized your mission. We have also configurations that have a cable-mounted transducer. This makes it easier. So instead of having the integrated transducer directly on the housing, this is a unit that can be detached and placed on a different location. So it's practical in case you need to integrate the modems or transponders to ROVs or AUVs. And as an example, final example, the optocoupler option. This allows you to switch on and off external devices by sending an acoustic command, and you have this output option from the modem that can be used to control other devices and sensors. Finally, I'll discuss about our acoustic modem emulator. It's a tool that we use frequently to test our own software and our own firmware for the modems. This is a virtual modem practically, but this is also a great tool for some of our customers who have application where they need to test their software to see how it will interact with our modems. What happens when you send some data? For example, typical application, you have the control software for an AUV. You are becoming information from multiple sensors, and at the same time, you're transmitting that information to the topside unit and becoming perhaps some commands and so on. So you want to be sure that this will work well before you try it in the water. So you can see what happens under different scenarios, all in the simulator, and see if your software can cope with all these situations. And if it does, then when you go to the water and test, you have a very solid basis to think that everything will work, or your biggest issues will be solved by then. I'll show you now how you can use, for example, the emulator. So this is our acoustic modem emulator that we ship with all the devices that we sell. This is, you can also download it from our website. And basically, I'm connecting different modems here. And this is a tool that can be used to test the communication between modems and also do some diagnostics on the communication. So for example, we have a small chat tool here. So if we have different modems and I send this message, I can select here who should receive it. I can send broadcast messages. And when I send this, I'll get some report information about what happened when this message was delivered. I get some information about the distance between the devices. So this was a very short message, so I don't get a lot of information. But if I send another slightly larger file, then I can get some additional information during the transmission. And of course, what you are seeing here is all simulated. I'm connecting to virtual modems that exist in our acoustic modem emulator. But I can see here things that resemble very much what happens in a real transmission. So in this tool, AMA, we are looking at what the integrity values are. We can see in real time also what the bit rate is doing. We can see that in this emulator, the distance between the devices is changing continuously. This is another thing that we can simulate in our emulator. You can also see the simulated multipath characteristics of the signal. You see that there are multiple signals arriving at the time. And so all of this diagnostic information is available with this tool and can be helpful if you are debugging your own application. You can also see here what is happening at the modem, what commands it's sending in order to retrieve all this information and when it's sending data. So it's a very practical tool that we recommend also to our customers who are developing some software to try, and can help you very much with solving issues that may present when you are in the water. You want to avoid having them when you are already in a vessel. You can do this in your office, which will save you a lot of resources. So this acoustic modem emulator, we usually have a subscription to it, but if you want to try it out before buying modems, you can contact us. We have a trial period available. I think, yeah, all of this I have mentioned already. You can test different scenarios. You can also test different sensors for compatibility. And in our webinar about sensor integration, I mentioned a little bit more about that. Software development and testing multiple scenarios. We simulate different things. The signal propagation delays, for example, if you are at a longer distance, the signal will take longer to arrive. Data packet collisions, packet synchronization errors. So things that happen in real life are simulated here. And you will have a very near reality feeling of what happens when you are using actual hardware. The good thing about the emulator is when you have the actual hardware, you can simply substitute the emulator for the real hardware and it will work the same way. So this is basically our webinar for this occasion. We will have some time now for some questions and answers. I would like to give you some information about our upcoming webinars. So as a complement to all of these webinars, we have a webinar on underwater acoustic positioning coming up on July 8th. Then we have another one, if you are interested in sensor integration, what you need to consider, how to optimize and so on June 30th. And of course, we will be glad to be able to finally see you in face-to-face occasion. The next event that we are planning to attend is Ocean Business in Southampton in the UK in October 12th to 14th of this year. Clear? So we invite you again to the next events that we are having, and thank you very much for joining us today. If you have any questions, please visit our website. You can use the contact form there or contact us directly at sales@evologics.de. We will be glad to be able to help you with your projects, or if you have an interesting application you are developing, we can also help you with some ideas and optimizations. Thank you very much. Looking forward to the next time.